Section 2.2, polynomial functions of higher degree. What we're looking at in this section is really just kind of one little piece in describing the behavior of functions. So my really big focus is going to be making sure that we are writing about these functions in the correct way. Remember, mathematics, it's a language. You have to be able to read it, you have to be able to write it in order to make sense of it and truly learn it. So today we're really focusing on writing about some of these functions. So the first thing we have to understand, polynomial functions are continuous. And that means what's called kind of, informally, it's called the pencil test, which means when you go to draw x to the third, okay, I never have to lift the marker off the whiteboard to draw that. It's one continuous smooth curve. When I go to draw x to the fourth, it comes down, it flattens out, it goes back up. Again, one smooth continuous curve. F of x equals x. One straight line, no breaks, no holes. That means there are no jumps, there are no holes in the graph, there are no asymptotes, there are no gaps like you'd see in a piecewise defined function. That means it's continuous. It's always moving from left to right in a predictable manner. Now when we have that predictable behavior, we start to see some similarities. Functions that are odd degree, so your x to the third, x to the fifth, x to the seventh, x to the ninth, those have opposite end behaviors. That means that as you go to one side, the function may go up. As you go to the other side, you see the opposite. The function goes down. When you have functions that are even degree, that means they have symmetric end behavior. Both sides go up or both sides go down. And you can even see that with linear. Linear is technically x to the first. That is odd degree, so you have opposite end behaviors. So end behavior, or what the function does to the right and to the left. That's determined by two things. I just spoke about one of them, the function's degree. Is it even, so you have symmetric end behavior, or is it odd, so you have opposite end behavior? And then there's also the leading coefficient. Now that leading coefficient could be positive, it could be negative. What will happen is, if you think back to transformations of functions, the leading coefficient results in a reflection over the x-axis. So if you have a negative leading coefficient, all of this reverses itself. So behavior that was going down to the left would now be going up to the left. Behavior going up to the right would now be going down to the right. Reflection over the x-axis here would take that symmetric end behavior, both going up, and now they are both going down. This is called the leading coefficient test. And it's how we can talk about end behavior for polynomial functions. Now the actual math that's happening here is quite simple. What I want to focus on is the language of how you should be writing it. So to describe right hand and left hand behavior, or end behaviors, start with that leading coefficient test. Now we have a negative leading coefficient, which means it's reflected over the x axis. And we also look, we have x to the third. That's an odd function, so that means opposite end behaviors. So if we were to get a quick sketch of this, a cubic function, doesn't have to be perfect, just has to be the general shape that you would find. Because it's a negative leading coefficient, it's reflected over the x-axis. It could very well look something like that. It's going up to the left and down to the right. But it's not enough to just say up to the left, down to the right. We want to use proper mathematical notation. So we'll say f of x is approaching something as x approaches negative infinity. We'll have f of x approaches something as x approaches positive infinity. Now what I've done is I've just really written a template that you can follow. You write down exactly this, leaving these blanks. All you have to do is fill in the blanks because I've taken care of everything else for you. The function, the y values, are going up or down as x goes to the left, to negative infinity. And then the function, the y values, are going up and down, up or down, as x goes to the right, towards positive infinity. So all you have to do is fill in the blanks. Is the function going up? You'd fill in positive infinity. Or is it going down? You'd fill in negative infinity. Well, as we approach negative infinity, remember this is as we go to the left. We see the function's going up. So we'd fill in a positive infinity. As x approaches positive infinity, again, that is going to the right. We see it's going down to the right. So we have negative infinity. So the leading coefficient test, and then this template for writing your mathematical conclusions.